Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 1 for this week, and it really doesn't have a whole lot to do with meteorology, although it can certainly be used for some scientific explanations relating to meteorology. But I did not know a lot of this, and the background and who actually came up with these numbers and how long ago they did it. And I just found it fascinating. So I thought, I'm going to make that my bonus video today, and hopefully other people will find this interesting as well. So let's get started here. There was a gentleman by the name, and I hope I'm pronouncing this right, Eratosthenes, who back in 240 BC made a rather interesting discovery in terms of how long the distance was to go all the way around the Earth at the equator. Okay, so he was told that on the longest day of the year at Syene, Egypt, which is in southern Egypt, I'll show you a map in a second, it's now known as Aswan, the sun's rays shone directly into a well with absolutely no shadow. Okay, so at solar noon, the sun's rays were directly overhead and shining right down into that well, and there was no shadow whatsoever. This meant, of course, that the sun was directly overhead. And it turns out that this was at the 23.5 north or 23.44 north latitude on the longest day of the year, the first day of summer, and that's where that was located, and so the sun was directly overhead at that point. Okay, then at Alexandria, which is much farther north along the Mediterranean Sea, the sun on exactly the same day at exactly the same time cast a shadow at an angle of about 7.2 degrees, okay? And the only way this could be true is that the Earth was round. So the flat earthers out there were dead in the water at 240 BC, okay? We knew all the way back then that the Earth was round and not flat. So this is not a recent discovery, okay? All right. So here is a map of Egypt that I got off of Google Maps. Want to make sure I give them credit for that. And Alexandria is up on the Mediterranean Sea, and then Syene, which is now known as Aswan, in southern Egypt along the Nile River. And Eratosthenes actually hired somebody to step off. Can you believe this? Step off the approximate distance between Alexandria and Syene. And the distance they came up with was about 800 kilometers, okay? So now that we have that information, we can do some interesting twists with math here. So here's the Earth. I'm going to say Alexandria is there and Syene is there. Obviously, this is not, drawn to scale, but just trying to illustrate and show the computations that he made. And so here's the well. That's my poor man's representation of the well. And there were a lot of obelisks in Egypt back then, maybe still now. And so that obelisk, if it's perpendicular to the Earth's surface, is not going to be parallel to the well, okay? It's going to be oriented like this. So the sun's rays are coming in, and the sun's rays are parallel. And so these rays are shining directly into the well, so there's no shadow, but these rays here are casting a shadow, and the angle between the orientation of that obelisk and the shadow itself is 7.2 degrees, okay? And he was able to compute that by taking a look at the length of the shadow, okay, and then using basic trigonometry to figure out what the angle was. Okay, if you extend both of those lines, if you will, where the obelisk is and where the well was, and you extend those to the center of the Earth, then it turns out that that angle is going to be 7.2 degrees as well, okay? Because if you have two parallel lines, and we've got those, let's see if I cursor up here, this one here, and if you extended this one over in here, you have two parallel lines, and then you have what's called a transversal line here, that this angle here has to be equal to this one here, okay? So if that's 7.2, this has got to be 7.2. So now you can set up a ratio, okay, where you can say that 7.2 compared to 360, which is the distance all the way around the Earth, is going to be the same as the ratio of this distance, this arc length, if you will, here, from Alexandria to Syene, which they approximated as being 800 kilometers. And then x is our unknown. X is the distance all the way around the Earth, okay? So what do? You bring x over to the left side of the equation, you invert 7.2 over 360 to 360 over 7.2, move it over to the right, and you get 40,000 kilometers, which, if you convert to miles, is 24,854.848. And you know what the actual circumference of the Earth is at the equator as measured by modern techniques? 24,901. That's not bad for 240 BC. That is pretty incredible that he was able to do that. Now, one other thing that I thought you might find interesting is that if you look at the Earth as like an onion, and you start taking slices like through the middle and then higher up in the onion and higher up in the onion, and so the slice of onion that you're getting is getting smaller and smaller as you go up. So the radius of the Earth, or the diameter, okay, is widest at the equator, and then it starts to get less and less as you go up. So I thought it might be fun to calculate what the radius is at our latitude, which is about 36 degrees north latitude. So let's go on ahead and tackle that issue, and then we'll be done here. So there's the Earth, there's the equator, and I'm going to draw another line perpendicular to that. Let's call that maybe the international date line or something like that. All right. So we know that the radius of the Earth at the equator is 3,963.19 miles, okay? And then all you have to do, if you know you're at 36 degrees north latitude, is create an angle that is 36 degrees, and wherever that line intersects the edge of the Earth, that's where you are. So we're going to say that's where the Raleigh-Durham Airport is located, is right where that line intersects the edge of the Earth. Okay, so we want to find out what the radius of the Earth is at this latitude. Okay, we know what it is at the equator. Obviously, this is going to be shorter, but what's the actual value? Well, again, same principle as with the other situation. If this angle is 36 degrees, then this has to be 36 degrees, okay? And we know that this is a right angle here, okay, where these lines are perpendicular to each other. So now let's just review a little bit of basic trigonometry here. So here's a right triangle, and in this particular case, I made, obviously this angle is 90, and I made these two angles equal just for the sake of this example. So there's 90, there's 45, there's 45, you add them up, it's 180. This is the hypotenuse, which is the side of the triangle opposite the right angle, okay? This, with respect to this angle here, is the opposite side, okay, all the way over here, and then the adjacent side is the one right next to it. This can't be the adjacent side because this is the hypotenuse, okay? There's only one other candidate for the adjacent side, and that's this one down here. So the definition of the cosine is the ratio of the adjacent side to the hypotenuse, which would be this over this, and the sine is the opposite side over the hypotenuse. So that's this distance over this distance here. Okay, so let's go back to our example. We know that this is 3963.19. We're trying to solve for this, and we know this angle is 36, this angle is 36, and this one's 90. So the cosine of 36 degrees is going to be the radius at 36 degrees, which is what we're trying to solve for, this distance here, divided by the hypotenuse, okay? And we know what the hypotenuse is. Why or how? Well, we know that this distance is 3963.19, and the hypotenuse, all we've done is taken this line and rotate it counterclockwise like the hands on a clock, okay? So we know that this distance is 3963.19. We know this angle is 36, and we know this is what we're trying to solve for up in here. So that distance over the hypotenuse, which is the cosine of this angle here, and so the cosine of 36 is 0.809, and then we multiply both sides of the equation by 3963.19, and it turns out that the radius of the Earth at 36 degrees north is 3,206 miles, 3,206.288 miles, okay? So at the equator, the radius from the middle of the Earth out is 3963.19. By the time you get to our latitude, it's down to 3,200. And you know what it is at the North Pole? 0, okay? And so the radius keeps getting smaller as you start taking slices higher and higher in that onion, and eventually you get to the point where there's no onion left, okay? All right, I hope you found that interesting. Of course, I love math. I know some people absolutely despise it and hate it, but I just, going back to the first example, I just thought it was remarkable that this guy could figure out all that with pencil and paper back in 240 BC. That's pretty good stuff. All right, folks, that's it for now. That's bonus weather video number 1. Next one will be coming up on Wednesday. Next daily weather update coming up tomorrow. You all take care. We'll talk to you soon. See ya.